Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I'll give a quick intro. I'm Bill Freeman. I'm a consultant for Microsoft and a colleague of Ted's at MIT. Ted's different than the rest of us.
He has really weird students, right?
Yeah, that's number one, yes. I'm a former student of Ted's. So many of us go off and write programs and do a lot of math and scurry around doing that. Ted goes off and he thinks about things, or he plays with things. And as a result, he has a lot of thoughtful and playful papers, which have had a lot of impact. I should mention, as a strategy, I think it's worked out really well for Ted. He's gotten a lot of recognition. Most recently, he's become a member of the National Academy of Sciences. Anyway, I really enjoy his talks, and I'm delighted to introduce Ted Adelson, who will tell us about material perception.
All right, thank you, Bill. So what Bill failed to mention is that I don't program or do math because I can't. And I've been forced to do other things, but fortunate to have good students who can do that stuff that I can't do. Okay, a lot of people think that vision, when you ask, well, what's vision about? They think vision is object recognition. This is very frustrating to me because I think vision is about lots of stuff besides object recognition. And this picture illustrates the idea that if you ran a successful object recognition system on this image, you would get something labeling that as a face and something labeling that as a dress or costume or something, whatever it is. We don't even know what it is, but we can tell a lot about the way it looks. It has this interesting sort of crinkly, looks like maybe it's made of paper or something. It's sort of shiny, sort of translucent. Whatever it is, we're just getting all kinds of information about it. And you know, if you were to describe this picture to a friend over the phone, so you could only use words, and you said, well, looks like a woman wearing a dress, and you can see her face. You know, there's just so much more. So if we want to simplify things, we can just say, well, the world is made of things, and they are made of stuff. And this is actually sort of instantiated in our language, where we have mass nouns like, let's say, wood or water or oatmeal, versus count nouns like chairs and people and bottles. And we tend to think of, for some reason, we tend to think most naturally of the world being made of these count nouns, the more classical nouns, but the world is also made of all this stuff, and our language and our perception recognize that. So this beginning part, I'm just trying to motivate why am I working on this stuff? Because of the fact that people think object recognition is everything. So what might material perception be good for? Well, if you're building a robot, suppose you're building a domestic robot that's going to clean up your kitchen, and it looks down and it sees something white on the floor down here, right? It says, oh, there's some white stuff there. And it might be salt that got spilled, in which case you can use a vacuum cleaner. The vacuum cleaner attachment to the robot can suck it up. But it might be a crumpled up piece of paper, in which case the vacuum cleaner might get jammed if you sucked it up. Or it might be some glob of cream cheese, in which case if you tried sucking it up with a vacuum cleaner, then you would have to find another domestic robot to clean up the first domestic robot. But for us, it's trivial to tell what these different things are, and to understand something about how they behave, what we could expect them to feel like or do or whatever. This is kittens licking up spilled milk.
And they know the difference.
And they can tell, right? Okay, and even though this problem has gotten very little attention in human vision or in computer vision, but it's gotten a huge amount of attention in computer graphics. And the reason is that, well, I guess economically the reason is that the biggest deal in computer graphics is animation. And you can't get people to watch animation if you don't have compelling materials. And the most challenging thing has been and continues to be hair and skin, because they're so complicated and we're so sensitive to every nuance, and exactly how much it's worth to get the hair and skin right is, we can calculate that because this is a still from Final Fantasy, which is one of the most ambitious attempts to do a completely synthetic movie. And her hair, this is the lead character, her hair cost $8 million. That is, if you look at the budget for creating and rendering, all the animators, I think it was it was over $100 million movie, but some substantial portion went into her hair.
This is just for the material or also for the movement?
It's the whole thing, yeah.
So this
So
is
the
an
hair is complicated
example.
also for movement.
So this could be done better, right? The hair
Today, yeah, well, this is quite a while
does the
ago.
hair looks sort of like...
Oh, you don't like the hair after all that?
Why will they show
He says it to me all the time.
Well, and I thought if you spend a little more, it would be better, but it's...
Okay, well, at the time, maybe it would look better if it was moving. At the time, this was the world's best hair. Okay, so they went hair by hair. They actually made a physical model of every hair and animated them, and it was extremely expensive. But she had really the best hair anyone had seen at that time, and it was a movie. Yeah, it was a big deal animation, full-length feature film. And the other characters had much cheaper hair, and you could tell their hair really looked cheap. Anyway, so just an example how we've got this contrast between people in vision who are not working on this problem and people in graphics who are constantly grappling with this problem. And so I'm a person in vision. I do some computer vision and some human vision, and I've been trying to understand something about material perception over the last number of years. And I think there's a good reason why not too many people work in this area, which is that it's hard, and I've been surprised that it's even harder than I thought. But I'll tell you some ideas we've had and some progress we've made. Oh, and just to say again, because of the fact that people in vision, and especially machine vision, have focused on getting their machines to recognize things rather than recognize stuff, we're in this situation where even a small child can look at a bowl of ice cream and see what it is, recognize it's ice cream, whereas today's robots can only recognize things like spoons. But we're trying to make progress to where they can recognize ice cream.
Did you draw that picture?
Yeah. I know it's not as good as Aki's hair. Okay, just to situate material perception, how is it different from other things? Well, obviously it's different from object recognition, or in this case, character recognition. These have a sort of a spatial structure that even when you move them around, change their color, rotate them, and so on, there's something structural about them that remains the same. And then on the other hand, texture is another well-known problem. And these textures here, they're all different. Every one is different at the pixel level. They don't have any commonality at the level of pixels, but they all look the same. They all have some commonality of appearance because they all have something common in their overall spatial statistics. And materials are different because you can sort of tell material involves some sort of interaction of a lot of stuff, but it's not objects and it's not texture. It's something else. And what goes into allowing you to see this object, everything about it that you can see? Well, these are the, I can just list the things that you need to specify. If you're, for example, going to render something in computer graphics, you describe the object's shape, the reflectance properties of its surface, the distribution of the surrounding light, which is impinging on the object, plus the camera viewpoint, and from that you get an image. And if you were to successfully build a vision system that could take that completely apart, you'd have to take it apart into all those sources, which is extremely difficult because they get combined in an extremely complicated way. And presumably humans don't successfully actually decompose it completely, but we do certainly get a lot of important information out of it. And in some of our work, we've decided to simplify things by saying, look, that's too complicated. In fact, what happened is I kept year after year trying to get students to work on this. They would come to my office. They say, what projects do you have to work on? And I'd say, well, there's this problem of material perception, which is nobody has any idea how to solve, and I also don't have any idea how to solve. And you might work on it for 5 years, and at the end of it have nothing to show for it.
And that didn't scare them away.
And no one ever wanted to do that. So students today they're just lazy. Anyway, so finally I said, oh well, let's just use spheres. We'll say we know it's a sphere, we know where it is, we've got shape all figured out, and can we make sense out of that? And it's still a complicated problem. So spheres are nice because anytime you look at a sphere, in the image, what does it present to your eye? A circle, right? It's just a disk full of stuff. Every sphere that you see appears that way. And here is a chrome sphere. This is the same chrome-plated sphere. And it always appears as this disk. But in every image it looks different. The pixels are different. There's no kind of template matching you can do on the pixels that will, as there is for something like the letter A, there's no template matching you can do that will allow you to say, oh yeah, that's what chrome spheres look like. In fact, what is that distribution of light that's on the interior of the sphere? Well, it's just a picture of the world, right? Because the optics is very simple. Light hits the chrome and it goes off, well, it comes from the world to your eye. It's just a distorted picture of the world. And so the scene that you stick your sphere in is going to make every time you put in a new scene, it's a different distribution of light because the scene is different. Well, except for one thing. All of these have a picture of me right in the middle holding a camera. But people are just unaware of this. They just look at it and say, that's chrome. How do you know? Well, because it looks like chrome. It has that look. And so we'd like to understand something about that. Okay, so in general, spheres show us modified pictures of the environment. And so on the left, that's just a shiny mirrored sphere. And it's just, right, each ray that comes to your eye is bouncing off of some particular location in the room. And this is a sort of brushed metal sphere. And in that case, the roughness of the surface causes some random variation in the direction, but not a completely random variation. So it ends up being a convolution, just a blurring of the world, the surrounding world, the environment map that gets to your eye. And you can even think of a matte white sphere as doing the same thing, where the convolution kernel is extremely big. It's blurring together stuff over an entire hemisphere. At any rate, the interesting thing is we look at these, and in principle you could make this one look like the other two by putting it in the right room, as long as your camera wasn't visible, right? Because you just have to surround it with, you have to very carefully surround it with all the right intensities. But that just doesn't happen, because the world doesn't look that way normally. And here's an interesting point of view of thinking of the material perception problem as system identification. That's, how many people know what that means? That's a word they use in sort of estimation and control theory, meaning basically, I've got a black box, I want to know how it behaves. I'll put something into it, I'll measure what comes out of it, and I'll try to figure out what the parameters are of that box. And the simplest example would be like a speaker or an amplifier. You want to know the frequency response of this thing. You put some sine waves in, you measure the sine waves that come out. Well, we can think of the problem of material perception as being of that sort, because what we have is, in this case, we have this sphere, which we can think of as a process which acts on this input signal. The input signal is the light coming from the world. So this distribution of light in the world hits the sphere turns it into some other distribution of light, which goes to the eye. And you look at it, and when you're looking at it, you're not interested in what's going on in the world. You're interested in the properties of the, in this case, the sphere. You're interested in how it's modifying the world, even though you, when you do this, really don't care about and don't know about what's in the world. Now, technically, you might know about what's in the world, but the fact is we can take these things in isolation and show them to you, so you don't know what's in the world, and they still give this sense of looking shiny or matte or whatever. So the way we can tell what things are made of in terms of this reflective property is because the world has some stable statistical properties. The way that this surface modifies those things tells us about the surface. Anyway, and just an interesting observation is this. If you're setting up to solve this problem, if you're a normal, let's say, machine vision person setting up to solve this, the first thing you'll do is say, well, I want this problem to be simple, so I'll use a simple case, like I'll have a single light source infinitely far away, and everything else will be black, and I'll illuminate it. So that's simple, right? The math will be simple. But for humans, this one, which is illuminated by complicated light, gives a much more compelling sense of the surface. It really looks, this is the same sphere, just in different environments. The complicated environment seems to provide information that's much more informative for our visual system.
So the first picture here is supposed to be the single point source?
That's right.
So it's the same sphere?
I'm sorry? It's the same sphere. Yes. I mean, I can't quite, because the dynamic range of the display is limited, I can't really show you what it would really look like. So this would really be a very bright specular point if it were the real scene, but this is the best I can do. Yeah, so same sphere. This is the simple lighting, complex lighting. And this, we have other examples of this. Here we've taken some data from natural scenes. Paul de Bevec went around and measured the light coming in from all directions in an outdoor scene and in an indoor scene. And we rendered, these are artificially rendered under those conditions. We rendered them and then placed them against this random background, which has nothing to do with the illumination. They look pretty good. You can see this shiny green sphere. Here's a point source. Well, you could believe it, but it's not so good. Multiple point sources also don't look good. And we could say, well, the problem is we need to have the visual, the visual system knows that the world is, it's got this 1 over f. How many people know what that means, 1 over f? The statistics, the simplest statistical property of the world around us, the visual world, is that Low frequencies, big blobby slow frequencies, are more prevalent than high frequencies, the little detailed things. And it happens that it goes as inversely with the frequency. The amplitude goes inversely with the frequency. So the simplest model of the world is just that it's random noise with a 1 over f spectrum. And if we make a world like that, that also doesn't look good. Here's a synthetic world which actually does look pretty good. That's a rectangular source. That sort of synthetic scene captures more of the properties of natural scenes, although we don't know exactly what the critical things are. So Ron Dror was the first student who was willing to work on this problem, and he worked with me and with Alan Wilsky, who's a professor at MIT who does estimation and control. And I have to admit, I had rather fuzzy ideas about how we would approach this, and he wanted to formalize it so he would know if he got the right answer. And so you can do this as follows. So we took real spheres in the world, and here's how we set up the problem. Suppose that I've got, I forget how many we had. Let's say I've got 9 spheres. I'll call them A, B, C, D, E, F, G, etc. And these are Christmas balls. Some that just came the way they are, and some we painted. Anyway, so we've got these spheres in the world. And we'll put them in a bunch of environments, lighting environments, call them 1, 2, 3, 4, 5, etc. And so you'll learn, we'll teach the machine, oh, this is what sphere A looks like in this environment, this, and this. Here's what sphere B looks like in all those environments. And now I'm going to show you some sphere. I won't tell you which one it is. I'll show it to you in a new environment you've never been in before, but it's a real world environment. So you don't know what the input signal is that's creating this image, but you do know the general properties of images that come out of that sphere. So can you do it? And whoops, do I have? I guess I'm missing one picture here. Anyway, we did a very simple thing, which is take that circular image, stuff going around right at the edges is a little bit hairy, so we clip that off. We open the whole thing up into a rectangle, and so it's all sort of simple to do image processing on. We do a wavelet transform. We get some luminance statistics that is on the pixel intensities. Anyway, we get a bunch of statistics that we hope are going to be useful, and then throw it into a support vector machine.
So why do you project it onto a sphere? Since you do that in a machine, why do you project it on a square? Wouldn't it make more sense to project it actually onto a sphere?
Well, I don't know if you've ever worked in spherical coordinates, but it's really unpleasant. And it might be that's the best thing to do, but that's not what we did. And this is, sort of a first proof of principle project. And anyway, so that's what we did. And it's a small problem, right? We've made this whole problem very small. We've said we're just going to do spheres. We're just going to do these spheres and these environments, plus some new unknown ones, so that it's tractable. And we had some success with 5 features. It'll do really well, maybe too well. But with just 2 features, you can see it's doing pretty well. And it's interesting what they are. These are the 2 best features of the set we came up with. This one on the bottom is the 10th percentile of the pixel values. Basically, this tells you, we look at the intensity of the pixels as a histogram. We say, what's the 10th percentile? We're asking, how dark is the dark stuff? 10th percentile, that's the stuff that, among the dark stuff, how dark does it tend to be? Okay, so on this end at the origin, that's a lot of dark stuff. Dark stuff is dark. On this end, not so much dark stuff. And then this other axis is the power in one of the wavelet subbands, which is probably just a surrogate for overall high-frequency contrast. But anyway, you can see a bunch of different spheres tend to end up in different places. And it's informative just to look at a couple of examples. So matte white.
Do you not have the other three there because they didn't work as cleanly as these 6, or is it just too?
I think it's because, no, I think it's because at the time this picture was made, we were only working with this set of 6.
So that's what I was asking. Are these the best 6 out of 9, or you were just doing 6?
No, I think that this is just historical. We happen to have 6 at this time. But it's a good point. Anyway, so white matte. Why is it down in that corner? Well, because it doesn't have any sharp stuff, so it's low on the vertical coordinate, and it doesn't have any dark stuff. That makes sense, right? It doesn't have dark stuff because every point on it is integrating information over a whole large area, so every point is seeing some light and getting it back to you. Okay.
In terms of the shaft, it's not that low in the vertical, right? It's about the same as the gray shiny.
True enough. And so sometimes, so if you have in this particular picture, the thing has no shadows, but if you move the light in the right place, you will get some discrete shadows dividing the illuminated from the non-illuminated. So it does get
more noticeable on white than on gray, which is why it's still.
well, I think the gray shiny is tending to, creep up higher. So I think, they're not exactly the same. Anyway, chrome is the most interesting. We were surprised by this because of the fact that it's so far down on the black, because chrome, of course, is very reflective. But in retrospect, it makes sense, right? Because why should chrome have such black blacks? Because chrome is not mixing light from all over the place. Chrome is just showing you what's at each position in the world. There are some positions in the world where it's very dark, so they show up as very dark on the chrome. And of course, chrome has a lot of sharpness. Anyway, it turns out this is something that painters already know. If you look in their rule books for how to make something look like chrome, they'll say, you want to have some sharp edges and you want to have black stuff in there. So it's already been well known. Anyway, so that gave us some confidence that it's worth. We could make some progress on this problem, which has been so difficult. And we did make progress, but it's just spheres. So we're trying to look at some things that are more complicated. And here's an example of an observation you can make with something that's more complicated, but not too complicated. So this is a picture. It starts out as a 3D rendering from the digital Michelangelo project. This is a picture of St. Matthew as carved by Michelangelo. And we just took this picture, it's already a rendering, and ran it through 2 different lookup tables. And on the left, that's if you run it through a lookup table that's accelerating like this. So it's making it's tending to make bright outliers, right? The stuff that's bright gets very bright. It's a point non-linearity. It's a function that it's just a single function. You have input intensity, output intensity. Does point non-linearity do better? Anyway, the lookup table is just an implementation of a.
So point means it's pixel by pixel.
That's right. Also called a static nonlinearity.
So it like maps x to x squared or x to square root x or something.
Yeah,
like that.
that would be an example. Anytime you can describe, it's just a one-dimensional function, right? You've got one number in, you've got one number out, and they're related by some curve. It's interesting how different audiences find different stuff obvious. I mean, it's just jargon, obviously, but I never know what's going to be the right jargon. Even between the vision world and the graphics world, they have totally different jargon. For example, people in vision would call this, a point non-linearity, they would call this a completely local operation because it depends only on what you're seeing at exactly this point. And people in graphics call it a global operation because it's done uniformly on every point. So, anyway. So we wanted to make some stimuli that we could experiment with. And so we made stucco. If you go to the art store, you can get acrylic paint with these various kind of thick and thin media. And you can make them dark and light and shiny and matte. Anyway, so we made this. We took pictures. And
I guess in hindsight it's obvious, but it's shocking.
What's shocking?
That the mean luminescence is the same. I mean, that's just...
Oh, yeah. So, well, I've adjusted the luminance on the screen so they're the same. But the point is simply that the overall appearance of the white stuff and the shiny black stuff is just very different. The mean luminance is not what's determining whether it looks black or white. It's something more complicated about the statistics coming back to you. And this is...
On purpose use a different pattern?
No, these are just what we randomly did. And actually there's a variation of this. I don't have the picture here, but I suppose we did this with white and black socks. We hung a white sock and a black sock in isolation in a dark room. And then you shine a bright light on the dark sock and a dim light on the white sock so that their mean luminance is the same. The average number of photons coming back is the same. And they're just sitting there in isolation. They look totally different because of the difference in the way the light scatters and bounces around. It leads to a very different appearance. Okay, so here's just some simple statistics, which we can do either on the pixel values, the luminances, or on the outputs of filters like Gabor filters. I should say, to calibrate this audience, how many people here know what a Gabor filter is? How many people know about wavelets? All right, so a Gabor filter is a particular kind of wavelet that's popular in the vision community. Anyway, and it turns out, they're useful for studying vision. So, but let me just say, statistics, you all know this, right? You have a distribution. In this case, this could be a distribution of pixel intensities or a distribution of outputs from your filter. And you can vary the mean, or you can change the variance, make that wider. You can change the skewness. That's this asymmetry thing that says there's a clump of stuff at the lower values and then this tail of outliers. And kurtosis is this very popular these days measure of kind of sparseness, of how much there's a tendency to have a small number of things near zero and then outliers at both ends.
So are there some experiments on humans that tell us how many moments we are perceiving with any to any significant extent?
Well, probably. I think no, not really. I mean, there's some evidence that we're sensitive to these kind of moments. The question is what comes next, and it seems like moments probably run out of steam as an explanatory method. It's just not the right vocabulary in general, but they're helpful for these.
So these are just global averages, right? Mean is sort of just the average intensity of the whole picture.
Right. Variance is the average of the square.
Right, but he's saying it's over the, it's not.
That's right.
over
These
the
would be taken
small
over.
areas of
Could be
the-
taken over attached. Could be taken over the whole thing.
No, but it doesn't refer to locality. So, like, if you were to permute the pixels, it
That's-
will give you the same thing.
If you're working on pixels, yes. Right. If you're working with wavelets, then if you scramble the pixels, you'll get different answers. Anyway, it turns out that skewness of either the pixel histogram or of the subband histograms, the wavelet histograms, is interesting for these kind of images because, and they're stucco. First of all, I don't show this here, but just physically in the world, if you measure the statistics, the blackness and shininess tends to lead to positive skewness, and the light color and matte tends to lead to either 0 or negative skewness. And then perceptually, we find the same thing. This is these are the results of some perceptual experiments where we just show people a bunch of stucco and we say how light does the color look or how glossy does the thing look, and then we measure these, just measure the skewness, and find a good correlation. This is not to say that this simple number predicts perception in general, but it seems to be an important thing to know about. And it turns out, in particular, this subband skewness is something you could very easily measure with a physiological mechanism. In fact, right at the retina, if you look at the ganglion cells, which are the cells that are sending information, sending signals down the optic nerve to the brain, they're organized in this center-surround manner, meaning they respond positively to light in their center and negatively to light surrounding them. So they tell you the difference between what's in the center and what's in the surround. There are actually two kinds. There's the on-center and the off-center, which are telling you about bright stuff among dark or dark stuff among bright. And if you just run this sort of thing through a non-linearity and then take an average and then take a difference between those, you can get a quick and dirty measure of skewness. And so you can, the red here indicates positive skew and green negative skew. So it's not something that would be difficult or complicated to measure. In fact, it's trivially easy to measure in a physiological system. And another sort of tantalizing bit of evidence comes from an after effect. So many of you probably know the motion after effect, where you look at something that's moving or, say, expanding for a long time, and then it stops and it looks like it's going the opposite direction. People consider this is because you're fatiguing some mechanisms in the brain, and normally they're balanced, and then when they get one of them gets adapted or fatigued, the balance shifts the other way. And we've done this with skewness. We show the subject an image which is skewed one way or another. This is positively skewed, negatively skewed, and have them adapt to that. And then we show them stucco afterwards. And we can, after we do this, we get slight changes in the shininess or the lightness of those of the stucco they're looking at. So there's, again, tantalizing evidence for some mechanism in there, simple mechanism that's involved. And again, this very simple thing, just these subband statistics, may be useful for interesting things. Let me just show you one example here. This is a picture. I don't remember why I processed this picture. This is a picture I found on Flickr of a guy's sweaty cheek. And sweaty, stubbly cheek. The question is, what happens if you, you build a subband pyramid, like a wavelet pyramid, take all the medium and high frequencies, put all the positively skewed ones on one side and all the negatively skewed ones on another side, reconstruct the image. So you've got, you've sort of divided the influences out. So here's what we get. This is the positive side. This is the stuff that comes through the positive skewness filters, and this is the negative side. And you can see, well, yeah, this is the lights, local light stuff is coming through on this one, and the local dark stuff is coming through on this one. In this particular picture, which was just a lucky picture, it happens that that corresponds to some meaningful things. The sweat in this case, the stubble in this case. But just an illustration that even these very simple measurements may be able to get us some useful information about what's going on in a scene. Okay, so this is just summarizing. This is summarizing this part of the talk. Just to say those statistics are useful. And now I want to tell you a little bit about some recent work where we're trying to go the opposite direction. What we started doing at the beginning is we were going to look at these very simple scenes like spheres and stucco, and we'll see how far we can get measuring simple properties. But ultimately, we want to get to the real world. And the real world is extremely complex. And humans are extremely good at making sense out of it. And so the first thing we did, this is work with Se Liu, who's now at Microsoft, and Lavanya Sharan, who was a grad student. So we built this database. Again, we went to Flickr. These are all Creative Commons pictures, so we can use them. And we have 10 material categories, which are, 6 of them are shown here. They're common categories: fabric, glass, metal, foliage, leather, paper. There's also water and what else? Stone, a couple of others. So now we're saying we're just going completely the opposite direction. First of all, we're not looking at these simple kind of parameters. We're not looking at qualities like lightness and glossiness. We're looking at identity, category. And secondly, we're looking at very complicated, in fact, intentionally complicated pictures. We didn't look at a classic picture of fabric or a classic picture of glass. We looked at pictures that where it was recognizable but still highly variable. So this is so that neither our humans nor our machines could get away with some stupid trick like saying, oh, if it's high frequencies, it must be fabric. So anyway, we attempted to make a very challenging database.
Categories are given to you or you label them?
We have, so it's an interesting problem because, of course, we didn't take the picture, so we don't know what the ground truth is on these categories. We look at them, and we also look at what the author said, or the photographer said about them. That gives us our ground truth. But it's not a true ground truth. Anyway, so we've got 10 categories, which we just chose because we were able to find enough Flickr pictures, and 100 pictures in each. And then we showed them to people, and people can do pretty well. And one of the things, initially we expected that people would be slow, because sometimes when you're looking at materials, you are slow, right? You're looking at at a flower, and you say, well, is this a real flower or a fake, or some leather? You say, is this a real leather chair or a fake leather chair? You may take a while and sort of scrutinize it. And we thought that might be typical, but it turns out people are quite fast most of the time. And just to figure out just how fast they are, we compared them in 2 tasks. So the first task, well, actually several tasks. First of all, we said, let's just take the simplest possible visual task we can think of, because there is, the reaction time to make a decision has to go through your brain and down your arm into your finger into the button, which takes a few hundred milliseconds. So even a very simple task takes a little while. Anyway, so we had a just picture of a diagonal line. Is it going this way or that way? That's the decision they had to make. as fast as they could. Or it's a blue dot versus a red dot. That's very simple. They had to make, those are two really simple decisions. We measured how long that took. And then we gave them these pictures of materials, and we said, is this paper or not? They would do a block of paper, paper or not, paper or not. Anyway, so the first one is this is the two diagonal lines. That was really fast. The two colors also pretty fast. But here, this green thing, that's the materials. Not as fast, but still amazingly fast, because look at what you're showing. You're showing people these pictures, and they have to almost instantly figure out what that is, in spite of the fact that it's a very weird, often very complicated picture. But people are quite good at it most of the time. The blue stuff is experiments that was even more challenging, where we actually had these real versus fake problems. We had like real flowers versus fake problems. That took even longer, but again, not really long.
Did they say yes, or did they hit a button? I mean, how did you...
They hit a button, yeah.
Okay, so if I'm slow in hitting the...
But then you're uniform.
But yes, so the idea is that the fact that you're doing a visual experiment and hitting a button is all sort of controlled for, because you had the very simple task at the beginning. People have done more complicated things where instead of hitting a button, you move your eyes, which is much faster, but we didn't go to that kind of experiment. Okay, here's another thing, just testing human capabilities here. We show them these pictures, and we show them, first we say, just take as long as you want. People do pretty well. Then we say, okay, we're only going to show it to you for 1 second. We see how well people do. Then we say, okay, now only 100 milliseconds. And at the end of 100 milliseconds, there's a noise mask, just this thing that comes up and splat, kind of make it impossible to continue seeing the picture. And then we do even worse things. We blur it. We get rid of the color. We blur it. We even invert it, so it's a negative, just to see how bad people will be when we do all these challenging things. People are amazingly good. Okay, so even with unlimited viewing time, they're not 100%. That's kind of weird, but it's because of the fact that, maybe according to the photographer on Flickr, this was a plastic glass, and they said it was a glass. Anyway, but they're up at 90%. We give them only 1 second. That's all of these ones here. 1 second. They're still up at 90%. We take away color, just grayscale. They drop a little bit. Still, we were very surprised at how well they do. We blur it. They drop a little bit more. Still, remarkably good. Chance is down around 10%. And then we, even inverting it.
These are people, like the grayscale, these are people who never saw the image in color.
That's right. Every image people see only once.
Okay.
They have to categorize it.
Tell them that you might invert the image or not?
I'm sorry. I should say these are blocked experiments, meaning they're in one condition at a time. So they get a whole series of things that have color, and then a whole series of things. So they understand that they don't have to completely switch what they're doing. They're getting a totally unexpected picture on each trial, but the fact that they're now in a blurry trial is something that they've had a sequence of the same type, so they're used to it.
And the IRB lets you show them a blurred image.
Yeah. As far as we know, we didn't do any damage. Okay, our 100 milliseconds. Again, it makes it worse, but still, it's amazing how robust people are.
So how many levels of visual processing does 100 milliseconds correspond to? Plus is there
Okay, so they're looking at a blank screen. The image comes up for 100 milliseconds.
Oh, I see. So
And then it goes off, and a random image of random noise comes up.
they only see it for 100 milliseconds.
Yeah.
Okay, so it's not the reaction time to hit the button.
That's right. No. This is the duration of the stimulus.
I see.
And And do we know how many frames I take per second?
I'm sorry.
He's asking how many frames can we process
Oh.
per millisecond or per second?
Well, I mean, we don't have a discrete, we are not processing things in discrete frames. And so different tasks take different amounts of time.
But there were these experiments in the 60s to show people sort of advertising in sort of for a certain amount of milliseconds, which
Subliminal.
you didn't know that you saw them. But so do you have any? I just want to know what 100 milliseconds means.
100 milliseconds would be long enough that it would not be subliminal. You would always see that. Maybe, I don't know, 20 milliseconds, 30 milliseconds would be getting to the point where you really can't tell that you're seeing it. So from that point of view, it's long. It's definitely long enough to see something, but it's not very long. Okay, so anyway, so just establishing some basic stuff about human vision. What we've learned is humans are really good, even in challenging conditions. Which means if we want to build machines that can get anywhere near to humans, it's going to be a challenge, as usual. But anyway, so I'll tell you our first stab at this. So we did some stuff early on with just spheres where it was really simple, and now we're going to take a stab at these really complicated things. And now we have to bring out the big artillery, which means two things. One is we're going to take all these techniques from the object recognition, machine learning literature, and the other is we're going to ask Leah to work on it, which really, I was giving a poster on this earlier this year, and people come by and say, well, we're not really getting very high recognition rates, and they think, well, maybe you just didn't do a good job. And I say, but look, Leah is one of the authors. So if you don't know him, he's here. He's at Microsoft, and he's amazing. He's unfortunately not able to be here right now. Okay, so what do we do? And I should say, I probably know less about machine learning than anybody in this room. So don't ask me any hard questions. But we computed a bunch of features. Again, we don't know what features to compute, so we just computed a whole bunch that seemed promising, including color histograms, JET, that's a sort of a set of wavelet responses. SIFT, I don't know how many people know about SIFT. SIFT is a big thing in object recognition. It's the most popular thing for, it tells you about sort of local spatial structure. And some other things we made up. Curvature, edges. And then trained classifier, again, because I don't know anything about this, these are just magic words to me, and I'm sure all of you can tell me much more about what I'm talking about. But just to say, we adapted state-of-the-art techniques using the features we used. And what did we learn? Well, the best individual features were color and SIFT. So color doesn't mean just the overall color. It means this cloud of all these color measurements. And what we're showing here is all these different categories. The first bar is the performance on the training set, and the second bar is performance on the testing set. And you can see something not too surprising here, like for foliage, if you're looking at foliage, color is a very good cue. And for other things, it's not such a good cue. And then for one of them is the training, the training, and the other is the testing. Anyway, overall, we're getting 32% on the test with color. And with SIFT alone, we're getting 35%. When we combine them, fortunately, they're not completely redundant, so we get 44%. This is out of 10 categories. I actually don't know the answer to that. If so, we're here, he could tell you. But anyway, this is, when we do the color, these are just these two individual features combined, we get 44. It turns out all these other features, if you add them into the mix, they give only very small improvements. Not to say that they aren't any good by themselves, it's just that almost everything that we are able to get, we've already gotten from these two. So, and by the way, we're not the first people to do anything with material recognition. There's some earlier work in using a different kind of situation. and we know that we're doing well because we can beat the prior algorithms. But, you know, are we doing well or not here? Well, bad news, we're not nearly as good as humans, but that's always true. And the good news is we do better than other people have done. And we're not doing totally different. It's not a total disaster. We decided that in order to get this published, because when we were working on it before, we were doing really miserably bad and nobody would want to publish it. We decided we would have to get up somewhere in the neighborhood of 30 to 50% in order to get people to publish it, to decide that, okay, there's something to actually work on here. So we managed to get that far. I'm sorry?
How large is the training set?
So I don't remember exactly how it was set up, but each category has 100, there's 100 pictures, and so I'm guessing that we did 50 for training and 50 for testing for each category.
And the feature set is around the same, like just 2 or?
Well, we start out with these, I forget how many, 1, 2, 3, 4, 5, 6, 7, 8, I guess 8 features basically. But each of those features is very high dimensional. And so, you do whatever, all these tricks that people do in the business to get the dimensionality down to the point where you can do training. Anyway, so that's the state of the art. And I just wanted to close with one more sort of inspirational thing on how far we have to go. Really simple experiment that just impressed me with what humans can do. So here's a picture, and this picture is what? It's a cupcake made out of yarn, right? Yeah. And the interesting thing is, it's right. So the material. This is just again to drive home the point. Material perception is different than object recognition because the object is a cupcake and the material is wool. But we showed pictures like these, and a strawberry. You're probably right. We showed pictures like these to people in these brief presentations, and we just asked them to say what they saw. So it's on for a flash. In this case, 300 milliseconds or so. And this is a good subject. Here's what she says. A wool cupcake, a knitted wool cupcake. So she's not looking at it now. She just saw it for a flash. So the cupcake part was made out of light brown wool with small specks of yellow and a pink wool on top. So it looked like sprinkles with a red wool cherry. It's just amazing. She got all this in this glance.
Is there a point where people would, is there 50 milliseconds or something where people would, what happens first, the material or the object recognition?
I think the objects, they're successful with the object a little bit sooner than they are with the material.
So there is some point time out where they would say it's just a cupcake and we wouldn't realize that it's made out of.
Yes, usually that's true. So you just kind of see a blob, sort of cupcake-shaped blob, and then they can't do the material.
Is that a hat that Dana would wear?
Anyway, so just to sum up, material perception is a legitimate problem of its own. not object recognition, not texture recognition. In the early part of the talk, we looked at simple problems, simple objects and surfaces with simple statistics, made some progress there. Second part, we looked at these complicated, much more complicated database with more complicated measurements, made some progress there. We are making progress, but we are clearly just at the beginning, and there's a long way to go. So thank you.
Why 320 milliseconds? Is there something magic about 320 milliseconds?
No. You mean why not 300 milliseconds? We just we did a series where we started with 10 milliseconds and 20, 40. We did a binary series, so we ended up with 320 on the way.
So somewhere in the beginning, you said that this is sort of a problem of system identification as opposed to just recognizing some characteristics in the vectors.
Yes.
I'm wondering if that's sort of, if that was true, if that's an accurate way of separating material perception from object and texture recognition. Is that really the prime difference, you think?
Well, I think that system identification thing, that's true for simple objects where the material is sort of expressing itself just through its reflective properties, because there it's how it's interacting with the world. But cloth looks the way it looks for all kinds of reasons, including how many fibers there are, its mechanical properties, the way it deforms. So when you get to these more complicated things, the more high-level stuff, it's a huge number of things. It's much more complicated than the surface reflection problem. Yes?
What's your opinion for the relationship, say, between material perception and more high-level tasks like object recognition or, say, like deformable models, or because at the beginning you're discussing these things about recognizing ice cream or things like that. So presumably those. I'm unaccustomed to working with high-level vision. I like to stay at low-level stuff where it's easier. And all I can say is, when you're looking at something like that, or if I go back to the database, when you're looking at these things, you're bringing in just all kinds of knowledge. I mean, you look at this, right? First of all, you might recognize, oh, that's a wrench. So wrenches are usually made of metal. You say, oh, that looks like rust. Rust kind of has that color and that texture. So seeing that this is metal involves a huge amount of knowledge and experience. And it's unclear where, is there a boundary between object recognition and material recognition, or between any of these things? It's not clear to me if there is a clear boundary. So the flip side of that question is, can you do well at material recognition for, say, pictures like that wrench without recognizing it's a wrench first? Right? If you just try to use these kind of low-level properties, are there a wide class of materials where you really have to figure out the object first and then?
Yeah.
Is there a way to test it in humans? I mean, I guess stopping the time at 100 milliseconds still gives time for people to bring up from the lookup table, bring up memory of what is a wrench. Because obviously they could even recognize that thing was a cupcake even before that. So
yeah.
So I guess if you wanted to somehow test if humans are able to
maybe
test
you could do
materials.
with children who know one set of information and don't know the other yet.
Yeah.
Somehow.
From agriculture.
Yeah.
Yeah.
So
children learn things at different times. Now they probably learn objects before they learn materials, but I don't know. But one could imagine that there would be a developmental stage at which they might know one and not the other yet.
So I have a couple of small children right now, so I've been noticing.
Does the IRB know about it?
It's very interesting, before you have children and after you have children, you have a very different concept of what
what the issues are that a child has to deal with. So, people think, you develop a visual system. People try to train like robots to recognize a pen by saying, showing this thing, pen. A robot is supposed to learn that's a pen. You see lots of examples of pen. But children begin by learning other things, like the pattern of light and sound in the room is such that mommy is probably going to come right now and give me some milk. Very, very complicated situational things. And then, for a lot of kids, including ours, their favorite object in the world is their blanket. And the blanket is just this thing that's some mushy shape. But if you've got some laundry and there's a whole bunch of clothing, all kind of these mushy shapes, and there's a little patch of the blanket showing up, the kid will say, that's my blanket. So, is that object recognition or is that material perception? Well, I think it's more material, really. It's really because they're not really seeing the whole blanket. And in a lot of these things, so in some cases, well, okay, so this is a frog, but it could be, made out of lots of different things and still have that shape. Or how do you know that this is cloth? You don't really recognize objects here. And in some of our data, we actually zoom in to make sure you can't really tell the object just by what you're looking at. And then you have things like, one of my favorite examples, how do you tell a bagel from a donut, right? Those are two different object categories, right? Bagels and donuts have almost nothing to do with each other, except for the fact that they now have cinnamon raisin, cinnamon, they have those sort of things. But when I was growing up, they didn't have those things. Well, the difference between a bagel and a donut is a bagel is made out of bagel stuff, and a donut is made out of donut stuff, right? So it's really a stuff recognition problem that allows you to do the object recognition rather than vice versa.
So another question. So humans, in principle, may be also learning to separate different materials by the fact that they were trained on video, not on images, right?
What are you thinking of?
And we are looking at images which are, we look at the same object over time, it changes in a slight way. Maybe at that time we get trained into recognizing different things and then eventually have enough of a database to apply to images. I don't know, does video recognition make any sense?
I'm just thinking of, I know one case combining all these themes where my my children have learned, they learn a lot from TV, actually. In fact, TV gets a bad name, but they really do learn a lot. Robin, who's 3.5, had a bad dream, came to her mother and said, "Mommy, I had a bad dream." She said, "What was it about?" "It was about a volcano." "Was there anything coming out of the volcano?" She said, "Yes, there was." "What was coming out of the volcano?" She says, "That stuff that comes out of volcanoes." So she knows from watching TV there's this stuff that comes out of volcanoes, which has its own unique identity and its own scariness. She doesn't even know a name for it. She just knows it's that stuff that comes out of volcanoes. I think it's probably true that kids these days are learning a lot from watching TV.
Did Madhu mean videos? I think he meant a sequence of images versus one image seen from different. It's the temporal aspect
I see.
which helps.
I see. That's a good question.
When you actually recognize, you don't need. Apparently, you just need this. But it's.
But our
So-
learning may be based
Yeah,
on
so
the
clearly
temporal.
we do learn a lot from the temporal stuff. It's possible that underlies our ability to set up these categories. If you have shiny objects, as you turn them, they glitter, they catch the light, very distinctive ways. If you have, if you have water, it has ripples. That's very dynamic stimulus. So yeah, clearly extending all of this to the case where you have multiple images over time it makes it an even richer set of problems.
This seems like you were unfair towards the computer in this data set, because like the people can use the fact that the glass is glass is made out of glass or a wrench is made out of metal. So did you try to see what? So you said in some cases you zoomed in, or so. How were people worse then when?
People actually were not much worse when you zoomed in to the point where you really couldn't identify the object. Mm-hmm. For something like this, again, it's a question of, is this object recognition? Suppose you're zoomed in like this. You can say, well, that's some metal thing. Mm-hmm. Now, you can't tell what thing it is, but are you recognizing it as an object, or is that material? At any rate, people are still pretty good when they can't label things.
That's a more fair maybe comparison with the computer, because the computer doesn't look at global. You don't have the global database.
But I think what's unfair to the computer is this: that humans have seen, especially adults, have seen millions of examples of metal and millions of examples of glass, and our computer only sees this very small set that we show it. And the space of, think of all the pictures of metal that you could see, and we give you 50 samples of metal. Well, they're sort of peppering this space very sparsely, and if there's any sort of continuum of metal appearance, it may be impossible to find with such small training. So that's certainly one of the things, is the fact that humans have this huge amount of experience. Yeah.
So if we had a challenge where you've got a person and a computer on one side, how smart are the computers nowadays? Are they smarter than a 1-year-old, 2-year-old, for material recognition?
Let's see. I'm trying to think, just back to my own kids. So I have pictures, I have videos, in fact, of one of my daughters at ages 1 and 2. And she, what she does, you give her something new and she plays with it. She manipulates it. She hears what it sounds like. She drops it on the floor, does all these things. She doesn't seem to, but she just doesn't know about very many materials. Most things, or objects, most things that you give to her are novel to her, and so she doesn't know what to expect. But she has this sort of a list of tricks that she does to try to figure out the behavior of this object and material. But that's one of the main ones. What does it taste and feel like in your mouth? But I think she's she's pretty sophisticated at being able to figure out how to manipulate it, but it took a long time for her to have a lot of experience with a lot of materials or objects. And for little kids, they really don't care about very many objects because there's no particular functional significance to, a toy truck versus a little house or something. Who cares? It's some object that if you're 1 year old, you can't do anything with it anyway. So.
What? He says odd and even numbers are much more useful. It's been 26 years since you've dealt with a 1-year-old person.
Yeah, maybe one thing you could try to test is to have a box out of a cube out of metal and a cube out of foam, and see if the kid, when it comes to lift it, he expects it to be heavy or expects it to be light. That could be a way to see if they kind of recognize that this is a different material. And
there is, I think,
you could probably watch the way kids.
There's a very.
They throw it at you.
What do they expect?
I think there's a very interesting moment that I think all parents have, where the first time you've put the kid in the bath and the stream of water coming down from the faucet, and the kid goes like this and goes, tries to grab it, and so clearly they do have expectations. All right, thank you very much.